Jensen Huang. Jensen Huang, known simply as Jensen, has been the CEO of Nvidia since its inception in 1993. He frequently uses a whiteboard to convey his ideas, which helps create a collaborative atmosphere. His detailed sketches often evolve into technical schematics, earning him the nickname Professor Jensen. At Nvidia, whiteboards are a symbol of innovation and the necessity to replace outdated ideas with fresh ones. The process of whiteboarding demands active thinking and reveals employees' understanding in real time, without relying on polished slides. Nvidia, which started as a small graphics chip company, has grown into a leader in AI processors. Its chips are particularly effective in AI tasks because they can perform multiple calculations simultaneously. Nvidia's early focus on AI and its strategic investments in hardware, software, and networking have positioned it to capitalize on the AI boom. On June 18, 2024, Nvidia became the world's most valuable company, driven by the high demand for its AI chips. Its stock has been an exceptional investment, with a compound annual growth rate of over 33% since its IPO in 1999. Jensen's leadership has been crucial, guiding Nvidia through challenges and fostering a unique culture. Nvidia's success stems from its organizational design, which combines independence, high standards, and a focus on the future, all driven by Jensen's vision and determination. Curtis Preem and Chris Malachowski. Curtis Preem learned programming by creating games in high school in Ohio. Preem chose Rensselaer Polytechnic Institute for college due to its advanced IBM 3033 mainframe computer. After graduating, Preem joined Vermont Microsystems, where he designed the IBM Professional Graphics Controller, a significant upgrade for IBM PCS. The lack of stock options led him to seek opportunities in Silicon Valley. Preem joined Genrad, one of the world's leading manufacturers of testing equipment for circuit boards and microprocessors at the time, but the company suffered from management missteps. Wayne Rosing at Sun Microsystems, impressed by Preem's work, hired him to develop advanced graphics for a new line of computers called the SparkStation series. Preem was given the freedom to design, leading to the creation of a powerful graphics accelerator. Chris Malachowski grew up in New Jersey, aiming to become a doctor. While taking the MCAT, he realized his true passion was engineering. After graduating from the University of Florida, he worked at Hewlett-Packard, gaining practical experience in manufacturing and chip design. Malachowski decided to do some practice interviews with other companies. One fortuitous session was with Preem at Sun Microsystems, leading to a job offer. He began working with Preem on graphics chips. Preem designed a graphics accelerator with 2 to 6 application-specific integrated circuits, the frame buffer controller for fast image rendering and the transformation engine for object manipulation. This setup allowed the graphics chips to handle most of the workload, freeing the CPU for other tasks. Malachowski needed to make the chip design a reality. Sun Microsystems didn't make its own chips, so he worked with LSI Logic, a leader in custom ASICs. Preem's designs needed more power for the SparkStation, so LSI took the contract and assigned Jensen Huang to manage it. Malachowski, Preem, and Jensen collaborated to solve problems and manufacture the chip. They finalized Sun's graphics accelerator, the GX, which improved display speed and enabled Preem to complete his flight simulator game, Aviator. However, Sun's culture became bureaucratic, stifling innovation. Preem and Malachowski decided to leave. They planned to create a new graphics chip, targeting the PC market. Nvidia. The PC market was growing in 1992 due to Microsoft's release of Windows 3.1 and the industry's adoption of the Peripheral Component Interconnect PCI bus, a type of hardware connection that transferred data among the expansion cards such as graphics accelerators, the motherboard, and the CPU at a high bandwidth. Preem had plans for a new PC-based graphics accelerator, which he called the GX Next Version, or GXNV. Jensen suggested dropping the GX, naming the new chip NV1. The co-founders worked out of Preem's townhouse in the San Jose suburb of Fremont. They set up folding tables for their equipment. Several senior engineers from Sun joined the startup, working without salary until funding arrived. Preem and Malachowski met with Jensen to discuss their business plan. Jensen was cautious but saw potential in the gaming market. They eventually agreed to embark on a new venture. Preem had no company name or funding, but he had an idea and the support of his friends. The startup needed a name. They settled on Nvidia, inspired by their chip name and the Latin word for envy, a callback to their work on the GX, when Priem and Malachowski believed that their rivals had envied their success. Nvidia was officially born on April 5, 1993. The search for funding began, with Jensen's connections proving valuable. Wilfred Corrigan, LC's CEO, introduced Jensen to Don Valentine at Sequoia Capital. Valentine decided to invest, influenced by Corrigan's endorsement and the potential of 3D graphics on PCs. Early challenges and triumphs. Nvidia finally began building its first chip. The company moved from Priem's townhouse to an office in Sunnyvale. Nvidia hired more staff, and the co-founders established roles. Priem as CTO, Malachowski leading engineering, and Jensen as CEO. Priem started designing the NV1 chip, aiming for high-quality graphics despite PC limitations. Memory costs were a challenge, so Priem developed a new software process called forward texture mapping to reduce memory needs, though it required game developers to adapt. Priem also enhanced audio capabilities. Nvidia partnered with SGS Thomson, a European semiconductor firm, for chip manufacturing. At Comdex 1994, one of the largest computer trade shows in the world, Nvidia showcased the NV1, impressing the Japanese video game maker Sega. This led to a partnership for the NV2 chip. However, Nvidia misjudged the market. Memory prices dropped, reducing NV1's advantage, and few developers adopted its graphics standard. The NV1 struggled with popular games like Doom, which relied on 2D VGA video graphics array graphics. Nvidia learned the importance of backward compatibility and market needs. They faced a cash crisis, realizing the importance of clear product positioning. Jensen aimed to learn from past mistakes to lead Nvidia effectively. He found insights in positioning. The Battle for Your Mind by Al Ries and Jack Trout, which emphasized that positioning is about influencing the customer's mind rather than the product itself. Customers often reject ideas that don't fit their worldview, but emotions can be swayed by the right message. Nvidia's NV1 had a complex message and couldn't compete with Doom-compatible products. This failure strained Nvidia's relationship with Sega, which canceled plans to use Nvidia's NV2 chip in 1996. However, Nvidia did secure a $1 million payment from Sega due to a contract clause. Nvidia had to lay off many employees and focus on developing the NV3 chip. Meanwhile, 3DFX, founded in 1994 by former Silicon Graphics employees, launched the Voodoo graphics chip, offering high-end performance at a consumer-friendly price. This chip excelled with games like Quake, boosting 3DFX's sales and revenue. 3DFX considered acquiring Nvidia but decided against it, believing Nvidia would fail on its own. Nvidia, however, focused on creating the Riva 128 chip, previously the NV3, which needed to compete with 3DFX. Jensen pushed for a larger, more powerful chip. Nvidia reused parts of the NV1 and licensed a VGA core from the graphics chip maker Widec to ensure compatibility. Nvidia launched the Riva 128 at the 1997 Computer Game Developers Conference. Engineers worked hard to ensure the chips could run the direct 3D graphics benchmark that hardware manufacturers would use to evaluate their quality. The Riva 128 barely passed the test, but it impressed enough people to generate buzz. The Riva 128 outperformed competitors, leading to significant interest and orders. Jensen used the Riva 128's success to secure more funding. He announced a major order from STB Systems, boosting morale. The Riva 128 became a hit, shipping over 1 million units and capturing a significant market share within 4 months. Jensen emphasized hiring smarter people and encouraged risk-taking. Nvidia's speed-of-light approach pushed projects to their limits, focusing on maximum efficiency. The Riva 128's development involved creating software drivers, specialized programs that enable the operating system and PC applications to interface with and use the graphics hardware before the chip was complete, saving time. This method became a competitive advantage, allowing Nvidia to stay ahead. The Riva 128's success set a new standard for Nvidia's future projects, ensuring drivers were ready at the start of production. Nvidia took control of graphics driver updates, releasing new drivers monthly to ensure optimal performance for gamers. Jensen often worked from 9 a.m. to midnight, and his team followed suit. The office was busy even on weekends. Jensen's motivational tool was fear. He often said, "We're 30 days from going out of business." This was to prevent complacency and prepare employees for pressure. Just months after the Riva 128 launch, Nvidia faced a threat from Intel's 1740 chip, which had an 8 MB frame buffer twice the size of the one on the Riva 128. Jensen declared that Intel aimed to put Nvidia out of business. Malachowski led the response, working on an 8 MB version of the Riva 128 to save the Riva series from obsolescence. Nvidia's focus on speed sometimes led to quality issues. The Riva 128 had some image quality trade-offs, leading to criticism. Nvidia also faced production issues with SGS Thomson, its chip manufacturer, leading to supply problems. Jensen secured production capacity from TSMC, the Taiwan semiconductor manufacturing company. By February 1998, Nvidia made TSMC its main supplier, launching the Riva 128ZX chip. However, production issues arose due to defects in TSMC's manufacturing. Malachowski suggested testing every chip. Nvidia hired contract workers to help. Still, Nvidia faced a production slowdown. Revenue dropped and expenses rose, leading to significant losses. Jensen sought financing from major customers, securing $11 million. Jensen restructured Nvidia to align with PC makers' cycles, releasing new chips every 6 months. Preem's virtualized objects architecture allowed for faster innovation, enabling Nvidia to emulate hardware features in software. This approach, along with backwards-compatible drivers, gave Nvidia a competitive edge. Nvidia's path to dominance. In 1998, 3DFX sued Nvidia for patent infringement. Nvidia's rapid chip releases outpaced 3DFX, whose slower schedules and quality issues hindered its competitiveness. 3DFX expanded its product line and acquired STB Systems to control its supply chain and increase brand awareness. However, its complex lineup and lack of a unified chip design contrasted with Nvidia's efficient strategy. 3DFX believed buying STB would harm Nvidia, as STB was a key partner for Nvidia's Riva 128 chip. However, 3DFX's strategy failed. They struggled with 2D chip production and lost other board makers to Nvidia. 3DFX's lack of experience in retail and manufacturing led to operational issues, and they couldn't produce high-performance chips quickly. Their Voodoo 3 was delayed, and they faced financial collapse, leading to Nvidia acquiring their assets and employees. Former 3DFX engineers were surprised to find Nvidia's success was due to hard work and strict schedules, not secret technology. Nvidia focused on hiring top talent, often poaching from competitors. Jensen recruited John Montrum, the chief engineer of Silicon Graphics SGI. Montrum's move to Nvidia attracted more engineers from SGI. SGI sued Nvidia for patent infringement, but the lawsuit was settled, benefiting Nvidia. Nvidia hired 50 SGI employees and became a supplier of their low-end graphics line. Nvidia ultimately gained a partner from the lawsuit. In the late 1990s, Preem started to clash with Nvidia's engineering team over chip architecture changes he made without informing others. Jensen, aiming for a communal culture, insisted on collective ownership of designs. Preem was eventually reassigned to focus on intellectual property. He left Nvidia in 2003, feeling outpaced by new talent. Jensen, still pained over the circumstances of his departure, believes Preem could have adapted. Nvidia went public in 1999, raising $42 million and providing financial security. The IPO allowed Nvidia to pursue strategic partnerships, leveraging its latest graphics cards GeForce to gain influence with Intel and Microsoft. Nvidia's relationship with Microsoft opened doors for the Xbox console. Although Microsoft initially chose Gigapixel for Xbox graphics, Nvidia's reputation and developer support helped them secure the partnership in 2000. Microsoft paid Nvidia $200 million upfront for the new chip's development. Nvidia's stock soared after the announcement. In 2000, Jensen and Michael Hara, who ran the investor relations team, met with investors to raise capital. Many investors feared Nvidia would fail. Jensen argued Nvidia's chips were superior and the company was innovative. Some investors believed in Jensen's vision, and the investment bank Morgan Stanley raised $387 million for Nvidia. The Innovator's Dilemma. In The Innovator's Dilemma, Harvard professor Clayton Christensen described how startups introduce a less capable but disruptive innovation at the low end of the market. Over time, startups improve their products and eventually surpass the established companies, which realize too late that they are in trouble. Jensen, influenced by Christensen's book, aimed to prevent Nvidia from being overtaken by low-cost competitors. He adopted a strategy to use rejected chip parts for cheaper products, increasing production efficiency. Nvidia was able to provide a variety of products and keep its market leadership by employing this ship-the-whole-cow strategy, which alludes to the way butchers find uses for nearly every part of a carcass. Nvidia branded its chips to stand out, naming the GeForce 256 as the first graphics processing unit GPU. This positioned it as essential, like a CPU central processing unit, making graphics chips more appealing to consumers. Nvidia's marketing team quickly adopted the GPU label to distinguish their chips and justify higher prices. The GeForce 256 was the first to be called a GPU, despite lacking features like programmability. Engineers disagreed, but marketing argued that future chips would include these features. The GeForce 256 still offered significant performance improvements, making it a category-defining product. The term GPU became an industry standard, helping Nvidia sell millions of cards. Modern graphics chips use a graphics pipeline to turn data into images. Early pipelines had fixed functions, limiting developers. David Kirk, Nvidia's chief scientist, wanted to create a true GPU with a new technology called programmable shaders, allowing developers more control. Jensen was concerned about costs but saw the potential. The GeForce 3, released in 2001, was the first true GPU with programmable shaders, leading to significant revenue growth. In 2002, a legal dispute with Microsoft over the next major update to Direct3D, called Direct3D 9, delayed Nvidia's access to the technical specifications needed for their next chip, the NV30. This forced Nvidia to develop the NV30 without proper guidance, leading to mistakes and poor coordination between teams. An Nvidia meeting revealed a missing feature called the fog shader and multi-sample anti-aliasing in the NV30, which ATI Technologies already offered. Nvidia's engineers were disconnected from market needs, leading to the NV30's failure. It struggled with Direct3D 9, causing poor game performance. A loud fan and high heat were major issues. ATI could have crushed Nvidia by lowering prices but didn't. Jensen realized Nvidia's internal teams weren't collaborating well, especially after integrating 3DFX employees. He learned from the innovator's dilemma to focus on internal culture, not just external success. Jensen resolved issues with Microsoft and ensured better communication with game developers. Nvidia survived its first decade, learning from failures. CUDA. In 2002, computer science researcher Mark Harris noticed that GPUs like Nvidia's GeForce 3 were being used for tasks beyond graphics, as they offered faster performance than CPUs. Researchers hacked GPUs to perform complex calculations. This method helped solve problems in physics and chemistry. Harris coined the term GPU general purpose computing on GPUs for this practice and created a website to share knowledge. His work led to a job at Nvidia, where he helped make GPU more accessible. Nvidia developed CUDA Compute Unified Device Architecture, a programming model that allowed GPUs to handle non-graphics tasks, expanding their use. Ian Buck and John Nichols were key figures in CUDA's development. Nichols focused on hardware, ensuring GPUs had larger memory caches. Buck worked on software, creating a programming environment for GPU computing. In 2006, Nvidia launched CUDA across all its GPUs. This move was costly, impacting Nvidia's profit margins, but Nvidia believed in CUDA's potential. Jensen emphasized the importance of CUDA in the coming era of the GPU. He saw it as crucial for Nvidia's future, even if it meant sacrificing short-term profits for long-term gains. Jensen's vision for CUDA required creating a market by analyzing industry needs and developing GPU-centered applications. Chief Scientist Kirk received requests from universities for support, leading to a program where Nvidia provided graphics cards and financial donations in exchange for using Nvidia hardware in classes. Nvidia established an internship program. Additionally, Kirk and his colleague David Lubke launched the CUDA Center of Excellence, offering schools CUDA-capable machines if they taught CUDA classes. Kirk taught a class at the University of Illinois in 2007, leading to the university becoming the first CUDA Center of Excellence. Nvidia then focused on non-academic researchers, giving GPUs to scientists and hosting technology summits for feedback. This approach helped Nvidia improve CUDA based on user input. Jensen emphasized the potential to revolutionize scientific research by making CUDA cheaper and faster. Biochemistry professor Ross Walker developed AMBER, a biotechnology program using CUDA, making it accessible to more researchers. Walker's work demonstrated the power of consumer-grade GPUs for scientific research, challenging the reliance on expensive supercomputers. Nvidia's annual report highlighted AMBER's success, and Walker was recognized as a CUDA Fellow in 2010. However, Nvidia recommended using the company's more expensive Tesla cards for AMBER, citing error correction features. Walker disagreed, proving GeForce cards were sufficient. He conducted tests showing no errors and suggesting Nvidia's recommendation was more about upselling than necessity. The conflict between Walker and Nvidia intensified when Nvidia altered the math precision in its gaming cards, affecting research tools. Walker and AMBER developers found a workaround, but Nvidia then restricted bulk purchases of GeForce cards. Walker criticized this move, fearing it would harm scientific productivity. Jensen expected salespeople to be self-sufficient and know their clients' needs better than the clients did. Nvidia's developer technology engineers supported customers, ensuring optimal use of products. The company never discounted its chips, emphasizing their exceptional value. CUDA's success is evident, with millions of developers and numerous applications. Nvidia's early investment in deep learning positioned it as a leader in AI development. The company dedicated substantial resources to creating CUDA-enabled frameworks and tools. The platform's compatibility and extensive support make switching to competitors challenging. Nvidia's strategic foresight and integration of AI libraries into CUDA solidified its market position. The Jensen way. Jensen's leadership style is direct, offering feedback publicly to foster learning. He believes in pushing employees to greatness and maintaining a focus on future challenges. Nvidia's structure promotes independence and transparency. Jensen manages a large team directly, ensuring alignment and responsiveness across the company. At other companies, talking to higher-level executives is discouraged, but Nvidia is different. Andy Keene, a former general manager for Nvidia's data center business, spoke with Jensen frequently and noticed Nvidia's open culture. Keene attended all board meetings, unlike typical companies where only a few people are present. Jensen shares important information with everyone at Nvidia simultaneously, encouraging feedback. This approach keeps the company flat, allowing information to travel quickly and empowering employees. Many large corporations are divided into competing units, leading to slow decision-making and short-term thinking. Jensen believes in a company that is large enough to do the job, but as small as possible, avoiding overmanagement. He created a fluid system focused on business goals, eliminating long-term strategic planning. Each project has a pilot in command pick who reports directly to Jensen. Picks have Jensen's authority and support, and employees are assigned to projects based on skills. Managers don't gain power from large teams, but from doing great work. Nvidia's flat structure allows quick decision-making based on data and merit. Jensen spends time explaining decisions and developing junior employees. Public feedback is efficient, offering learning opportunities. Jensen uses top 5 inches emails to stay informed, asking employees to share their top tasks and market observations. This helps shape strategy. Jensen responds quickly to emails, expecting thoughtful, data-backed replies. Nvidia's culture avoids internal politics and focuses on accuracy and rigor, enabling the company to seize new opportunities and thrive in a competitive market. Activist investor Carl Icahn believes many companies choose CEOs based on likability rather than competence, resulting in poor leadership. Steve Ballmer at Microsoft is a prime example. With a marketing background, he missed key tech shifts, causing Microsoft stock to drop. Similarly, Apple struggled under John Sculley, a marketing expert, until Steve Jobs returned. Intel faced issues under Bob Swan, a finance expert, who focused on stock buybacks. Nvidia avoided these pitfalls with Jensen, a technical CEO. Jensen leads with concise communication and a strong work ethic. He believes in being deeply involved in technology to make informed decisions. Jensen's approach focuses on big picture thinking without getting bogged down in details. He often works long hours and expects the same from his team. This intense work culture stems from Jensen's belief that success requires an obsession with work. Jensen's leadership has kept Nvidia innovative and successful. His blend of technical and business acumen sets him apart. Jensen's approach challenges the typical division between technical and business leaders, showing that one person can excel in both areas. In 1981, IBM revolutionized computing with the IBM PC, which had Intel's 8088 chip and Microsoft's MS-DOS operating system as key components. However, IBM failed to secure exclusivity, leading to a flood of cheaper PC clones from Dell and HP. This oversight forced IBM to sell its PC division to Lenovo in 2005. This mistake led to the close partnership between Microsoft and Intel, known as Un2known, which dominated the computer industry for decades. Companies built their operations around Windows and Intel processors. Microsoft adapted to cloud computing under Satya Nadella, while Intel missed smartphone and AI opportunities. Nvidia, led by Jensen, focused on GPUs and AI, investing in CUDA and acquisitions like the high-speed networking leader Mellanox. Nvidia's strategy contrasts with Intel's, emphasizing innovation over profits, aiming to lead in AI like Un2known did in PCs. The AI revolution. For decades, CPUs were the main computer chips, handling tasks sequentially. GPUs, however, excel at parallel processing, breaking tasks into simpler operations executed in parallel. This makes GPUs faster for many applications. In 2005, Kirk was ready for a change. He had been with Nvidia since 1997, helping the company through ups and downs. He needed a break, but had to find a successor who met high standards. He considered Bill Daly, a renowned computer scientist. Daly had an impressive background at Bell Labs, MIT, and Stanford. Kirk invited Daly to consult on Nvidia's Tesla chip, which used parallel computing, a field Daly pioneered. After a long courtship, Daly joined Nvidia in 2009, aiming to apply his theoretical work to commercial uses. Daly shifted Nvidia's focus to parallel computing. He collaborated with Stanford professor Andrew Ng, who used deep learning to teach computers to recognize images without human help. Ng's work required massive computing power, initially using thousands of CPUs. Daly suggested GPUs could do the job more efficiently. Nvidia's Brian Catanzaro optimized GPU use for deep learning, reducing the need for CPUs. In 2012, Professor Gary Hinton and his students from the University of Toronto used NVIDIA GPUs to win a computer vision contest, proving deep learning's potential. This success caught Jensen's attention. He decided to invest heavily in deep learning. Jensen had spent 2 decades preparing NVIDIA for this pivotal moment. As AI emerged, he shifted resources to focus on it. NVIDIA released AI-specific features, making all hardware compatible with CUDA for custom programming. Catanzaro developed CUDA Deep Neural Network CUDN, NVIDIA's first AI-optimized library, crucial for AI developers. NVIDIA also developed a new type of tiny processor for AI called tensor cores, enhancing deep learning efficiency. These changes were costly but necessary, as NVIDIA aimed to lead in AI hardware and software integration. Jensen recognized the importance of a comprehensive ecosystem for AI, making NVIDIA a go-to choice for developers. NVIDIA's strategic moves positioned it at the forefront of AI, with its hardware and software ecosystem attracting top researchers and companies. Starboard Value, an activist hedge fund, briefly invested in NVIDIA, advocating for stock buybacks and a focus on core assets. NVIDIA's acquisition of Mellanox further strengthened its position. Mellanox's technology became crucial for AI workloads, contributing significantly to NVIDIA's growth. The acquisition was a strategic success, enhancing NVIDIA's dominance in AI. Jeff Smith of Starboard Value later reflected that they should have stayed with NVIDIA. NVIDIA's edge. Light is a complex phenomenon, acting like both a particle and a wave. It can reflect, scatter, or be absorbed by objects. In computer graphics, light is crucial but hard to replicate. Early graphics struggled with realistic lighting due to complex calculations. Even with GPUs improving graphics, light remained a challenge. David Luke, with a PhD in computer science, joined Nvidia Research in 2016 to tackle this. Nvidia started a research group to solve complex graphics problems. Ray tracing, simulating light rays in virtual scenes, was a focus. Initially, CPUs were thought better for ray tracing, but Nvidia research showed GPUs could handle it faster. Lube's team demonstrated this, leading to Nvidia's interest in ray tracing for gaming and professional markets. In 2008, Nvidia showcased a demo, proving GPUs could handle ray tracing. This led to the development of Optics, a ray tracing engine. Years later, Nvidia revisited ray tracing, aiming for real-time applications. In 2018, Nvidia introduced Turing architecture with specialized ray tracing cores. Jensen suggested using AI to enhance graphics, leading to DLSS deep learning supersampling, which improved image quality. Nvidia continued refining the technology. DLSS 2.0 and 3.0 improved performance and image quality. Nvidia's approach to innovation involves fast product releases and long-term research projects. This strategy led to successful advancements in ray tracing and AI, transforming gaming and graphics technology. Nvidia has maintained an 80% share in the GPU market for a decade, despite AMD's competitive pricing. Jensen's strategy focuses on future-proofing Nvidia through continuous innovation. Nvidia's GPUs are crucial for AI, with companies like Meta and TikTok using them to enhance algorithms. In 2023, Nvidia's earnings report exceeded expectations, boosting its stock by 24% and adding $184 billion in market value. Jensen capitalized on this by announcing the DGX GH200 AI supercomputer, emphasizing Nvidia's superior computing power at lower costs. Nvidia's sales strategy involves convincing customers to invest in AI to stay competitive. The company's data center business saw a 427% increase, driven by AI chip demand. Nvidia's success stems from its ability to anticipate demand and prepare accordingly. The company employs a full-stack model, optimizing hardware, software, and networking, unlike competitors who only make chips. Nvidia's pricing strategy focuses on creating unique, high-value products, allowing it to increase prices over time. Nvidia's current hardware enables rapid AI model growth, with demand for computational power outpacing supply. Nvidia's top-end products are priced in the millions, reflecting their advanced capabilities. Jensen's vision and strategic timing have positioned Nvidia as a leader in both gaming and AI markets. Jensen believes digital biology will follow AI, allowing scientists to model biological systems digitally. Kimberly Powell from Nvidia says computer-aided drug discovery will revolutionize drug design. The startup Generate Biomedicines uses AI and Nvidia GPUs to create new drugs, with co-founder Gevorg Grigorian highlighting Nvidia's support for research. AI models now solve complex protein design problems, and Grigorian envisions AI-driven drug discovery. AI will transform how employees access information, with models understanding natural language. Goldman Sachs predicts AI could save more than $3 trillion in costs. Nvidia is prepared for future computing trends, with increased AI spending expected to benefit society. Driving excellence. Nvidia fosters a culture of excellence, with employees working on impactful projects alongside industry experts. Long-term commitment is common, with many executives staying for decades. The focus is on technology, not internal politics. Employees are encouraged to seek help when needed, promoting teamwork. Jensen prefers open workspaces over private offices, using conference rooms for meetings. He values hiring and developing talent that fits Nvidia's culture. Communication is key, ensuring everyone understands the strategy. A former executive noted Nvidia's consistent messaging, unlike other companies where employees often disagreed publicly. Nvidia aggressively hires top talent, often through employee referrals. When the sound card maker Creative Labs closed a location, Nvidia quickly hired the team without requiring relocation, showcasing its swift decision-making. Nvidia hires top architects from competitors, offering them resources and exciting projects. Employees receive stock over time, with additional grants for top contributors. The company also offers flexibility and assistance during personal crises. This approach keeps turnover low, with Nvidia's rate under 3% compared to the industry average of 13%. Nvidia's culture demands extreme commitment, with 60-hour work weeks as a minimum. Jensen knows employees personally, expecting high performance and continuous learning. His leadership style involves listening, understanding, and answering questions thoroughly. Jensen is now the longest-serving CEO in the technology industry. His approach combines technical expertise with strategic foresight. Jensen has fostered a culture where employees are encouraged to push boundaries and strive for greatness. Nvidia's success is not just a result of its technological advancements, but also its ability to anticipate market trends and adapt accordingly. By investing in research and development, Nvidia continues to lead in creating cutting-edge solutions. Nvidia is well positioned to remain a dominant force in both gaming and AI markets for years to come.